Representing some famous functions in terms of hypergeometric functions. So previously in my video, I have already introduced what uh, ordinary hypergeometric function is, and let me just define it right now as well. Hypergeometric function where 2 are on the numerator, 1 on denominator of, let's say, a, b, and c, and g. This is defined as sum going from n equals to 0 to infinity, and this is rising factorial of a or rising factorial of b by rising factorial of c, and then g to the power n by n factorial, where a rising factorial of n means that product from k to k plus n minus 1. Yeah. And this can also be written as gamma of k plus n by gamma of k. Before we begin proving these representations, and if you want more detail of these things, you can also find the video over here. And okay, so before we begin with proving these things, we need to know, I want to give you some ideas, such as what is 1 to the base n. This is actually 1, 2, 3, yeah. So basically, if we have 1 to base 1, this is just 1, yeah. If we have 1 base 2, this is 1 into 2. If we have 1 base 3, it is 1 into 2 into 3. That's why 1 base n is product up to n, and this is n factorial. Okay, so you know about this stuff now. And if let's say if we have 2 base n, this is n plus 1 factorial, yeah. And if we have let's say 3 base n, then this is n plus 2 factorial by 2 as well, yeah, because this starts from 3 up to n plus 2. Okay, so if you know this stuff, now you are adapted to be able to prove all of these statements. Let's begin with the first one, ln of 1 plus c. So we have okay, let me write it over here. So we have f 2 1 of 1 comma 1, so semicolon 2 semicolon minus g, and also note that we have a g outside. Okay, so that means a product. Now this can be written as sum going from n equals to 0 to infinity. I have this 2 in numerator, yeah, 2 over here also. So 1 base n, 1 base n, now this is numerator, 2 base n, and now minus g to the power n by n factorial, and all of this is multiplied by g, yeah. So now as I have already told, 1 base n is just n factorial, 1 base n is just n factorial, 2 base n is n plus 1 factorial, and this is minus 1 to the power n. If multiplied by g, we will have g to the power n plus 1 by n factorial. Okay, n factorial cancels out, and we have sum going from n equals to 0 to infinity, and then we have minus 1 to the power n, g to the power n plus 1 by, this is just n plus 1 over here. And we know that this is exactly the ln of 1 plus g series, yeah. So this is how we proved the first representation. Now let's go to the second one. Let us go from the last. That will be nice. Let's go with this one. This is ordinary hypergeometric function to f1, and then 1 1 semicolon 1 semicolon g. Okay, so this is sum going from n equals to 0 to infinity. This is 1 base n, 1 base n, downside also 1 base n, and then g to the power n by n factorial. Now we know that 1 base n 1 base n cancels out, and this is also n factorial cancels out, so we see that this is exactly geometric series, and if the modulus of g is less than 1, then I can write this as 1 by 1 minus g. Yeah, so we do the third one as well. Now let's go with this one, and then arc sin x. So basically I'm doing in the increasing order of difficulty. Yeah, now this one over here, ordinary hypergeometric function of a comma 1 in the numerator, 1 in denominator, g. This can be written as sum going from n equals to 0 to infinity. Yeah, and then we have a base n and 1 base n by 1 base n g to the power n by n factorial. Yeah, and now 1 base n 1 base n cancels out. So what do we have basically? Now a base n will be sum going from n equals to 0 to infinity, a plus 1 up to a plus n minus 1. Yeah, and over here we have g to the power n by n factorial. Okay, so now let's also look at how the expansion of let's also look at how the expansion of 1 minus g to the power minus a is, and then we will have the idea. So 1 minus g to the power minus a, we can basically use we can basically use the binomial theorem. Yeah, so from that what can we do? So first of all, we will just have basically sum going from n equals to 0 to infinity, minus a to n, and then minus g to the power n. Yeah, now for negative index, this we can make sense of this in this way. So minus a minus 1 minus a minus 2 up to minus a minus n plus 1. Yeah, by, now we also need to write n factorial over here, and this is minus 1 to the power n g to the power n. Yeah, so this is basically this is basically just the definition of combinations. Yeah, you might have like seen this in the cases where, let's say if we have 4c2, we write this as 4 into 3 by 2 factorial. Yeah, so similarly the case over here as well. Now there are n terms, and also we have minus 1 n times, so we can distribute each of them, and so we get sum from n equals to 0 to infinity, a plus 1, a plus 2, and up to a plus n minus 1 by n factorial g to the power n. So now we see that this is also the series of 1 minus g to the power minus a, and this was also the series that we got over here. Yeah, that's why we can say that this is actually equal to 1 minus x to the power minus a. And yeah, so we proved the third one as well. Now it's turn for arc sin x. Okay, let us prove this now. Let us do it over here. Oh, sorry. Let me minimize this. Okay, so now let us prove this. First of all, let us see what the series expansion is actually. Arc sin of x is actually sum going from n equals to 0 to infinity, and then we have 1 by 4 to the power n, or 2n choose n, x to the power 2n plus 1 by 2n plus 1. So this is the series expansion for arc sin x. Yeah, Now, basically, let me first of all let us find the alternative form for this 2n choose n, so that it will be easier later on. So 2n choose n is basically 2n factorial by n factorial. Yeah. Now 2n factorial can be written as 2 to the power n times n factorial. Let me simplify it. Let's not complicate. Okay, 2n factorial can be written as 2n 2n minus 2 2n minus 4 dot dot dot, and also 2n minus 1 2n minus 3 dot 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 up to 1. Yeah. And n factorial. Now if I take 2 common from all of this, I will have 2 to the power n times n factorial. Yeah. And now when there are gap of 2 between two consecutive factors, this can be written as 2n minus 1 times double factorial. This is basically the definition of double factorial, by n factorial into n factorial. Now I can cancel the n factorial out, and we can get that this central binomial coefficient 2n choose n is actually equals to 2 to the power n times 2n minus 1 double factorial by n factorial. Yeah. Now up to this we are good to begin. Now this hypergeometric representation, what does it say us? So basically sum from n equals to 0 to infinity, and then minus 1 1 by 2 base n, 1 by 2 base n by 3 by 2 base n. Yeah. And then g square g square to the power n, g square to the power n by n factorial, and also we have a g over here. Yeah. So now let us try to find these values. G times sum going from n equals to 0 to infinity. So this will basically be 1 by 2 plus 1 up to 1 by 2 plus n minus 1. Yeah. And this will also be 1 by 2 plus 1 up to 1 by 2 plus n minus 1. Yeah. And that will be 3 by 2 plus 1 up to 3 by 2 plus n minus 1. Or okay, fine, but and I will tell it on. Okay. And then g to the power 2n by n factorial. Okay. Now something to notice over here is, so basically this is also in this series as well. This is 3 by 2 plus 1, 3 by 2 plus 2, and those things are there. Yeah. And basically up to the second last term of this series, they cancel each other out. Yeah. So that's why what I have is sum going from n equals to 0 to infinity 1 by 2, and the last term remains, which is n plus 1 by 2. So 2n plus 1 by 2, this remains over here. And over here what remains is there are n 1 by n 2 is in denominator, so we have 1 by 2 to the power n. Yeah. And then there are 1 times 3 up to last one is 2n minus 1. Okay. And that is it. Now g to the power 2n, I'm really sorry for this thing that there's lack of space. Okay. And then so we have written it over here. This is over here. Now this one is over here. 2 is also over here. Now g to the power 2n by n factorial. Okay. Now g can be taken inside. Yeah. So we have sum from n equals to 0 to infinity. 2 cancel out, And one thing that I can do over here is I can change this to 1 by 4 to the power n, and this is just 2n minus 1 double factorial. And since I have written 4 to the power n over here, I can write 2 to the power n over here. By n factorial is also over here, and I can write 2 to the 2n plus 1 over here in denominator. I can take g inside, so I have g to the power 2n plus 1 by 2n plus 1. Yeah, so now we know that this is just the central binomial coefficient. So we have sum from n equals to 0 to infinity 1 by 4 to the power n, that is just 2n choose n, g to the power 2n plus 1 by 2n plus 1, which is the series expansion for arc sin x. Yeah, and we have proved this one as well. This one was somehow longer than the others, but yeah, we did solve it. Let me create the boundaries between these solutions. Okay, so till now we have done 4 of them. Yeah. Okay, so 1 2, and then this was the third 3 4. Yeah, fine. Now let us go with these others. For e to the power x, okay, for e to the power x, the hypersymmetric function is, there's nothing, only the z. Okay, so let's see how do we do that. We just have 2f1 of nothing semicolon nothing semicolon z. That means sum from n equals to 0 to infinity. We don't have any ABCs, so g to the power n by n factorial, and that is e to the power z. So this was so simple. Yeah. Now let's go to the next one. Nothing 3 by 2 minus g square by 4. Okay, so 2f1 nothing 3 by 2, and then minus g square by 4. Yeah, and then times g is also there. Okay, fine. So for this one, what we can do is sum from n equals to 1 to infinity. We don't have a's and b's, we have only c. So 1 by 3 by 2 base n, and then minus g square by 4 to the power n multiplied by g. Yeah, so sum from n equals to, so not this is 1, not 1, it's 0, n equals to 0 to infinity. So we have basically 1 by, this is 3 by 2 plus 1 up to 3 by 2 plus n minus 1. Yeah, and now this is minus 1 to the power n g to the power 2n by, this is 4 to the power n times g. Okay, so now what can we do next? This is g, so I'm going from n equals to 0 to infinity. What do we have over here? 3 times 5 times so basically now 7 and such things. I can add 1 over here by myself here, and this last thing will be 2n plus 1, and there are n 2's. Yeah, that's why we will have 2 to the power n over here, and then minus 1 to the power n g to the power 2n by, oh, and I think I forgot something. I forgot the n factorial, to write the n factorial over here. So basically I also need to write by n factorial over here. Yeah, I forgot that, n factorial. So n factorial now. Yeah, is that fine? Oh, and also there's a 4 to the power n over here. Now it's fine. So now I have g, so I'm going from n equals to 0 to infinity. Now this is, now I can cancel 2 to the power n with this one, and we'll just have 2 to the power n. Yeah. Now if I merge these two, 2 to the power n factorial, and write it over here, we just have minus 1 to the power n, and I can also take g inside, g to the power 2n plus 1. By now we have 1, and 1 times 2, 2, 3, 2 times 2, 4, 5, 3 times 2, 6, 7, and 2n plus 1. Yeah. So now what do we have? Sum from n equals to 0 to infinity. This is minus 1 to the power n, g to the power 2n plus 1 by 2n plus 1 factorial. And yeah, we all know what this is. Yeah, this is just the function per sine g. Okay, so now we have done it for sines as well. Now the last one is of cos. Okay, so for cos, you know, it's 2f1 dash 1 by 2, and then minus g square by 4. Okay, so now let's do it as well. So the only thing that's different is here's 1 by 2, here was 3 by 2, and now let us see how do we get the difference. Looks like we won't be getting the difference, yeah, but we will. Like even I'm not sure how we will. Okay, so let's go how do we and we will see how we get a difference. Sum from n equals to 0 to infinity. Now we don't have anything over here, so we have 1 by 2 to the power n, and then minus g square to the power n by 4 to the power n by n factorial. Okay. Yeah. After that, we have sum from n equals to 0 to infinity. 1 by, so this is 1 by 2, 1 by 2 plus 1, yeah, and then up to 1 by 2 plus n minus 1. Now this is minus 1 to the power n, g to the power 2n by 4 to the power n times n factorial. Okay, so now we have sum from n equals to 0 to infinity. Now there are n2, so 2 to the power n, and so we have 1 times 3 times 5 up to 2n, this is 2n minus 1, yeah, and then minus 1 to the power n, g to the power 2n by 4 to the power n times n factorial. Now there's a nice cancellation, 2 to the power n. Now we can merge this 2 to the power n and n factorial and then combine over here. That gives us sum from n equals to 0 to infinity minus 1 to the power n, g to the power 2n by 2n factorial. And we know that this is just cos of g. So we have finally prepared this one as well. So we did it for sine, cos, exponential function, geometric series, binomial expansion, arcsine x. Among all of them, arcsine was the most nicer one, and logarithmic function as well. So hope you enjoyed these representations, and in my next video I will try to show you how do we find these representations actually from Taylor series to hypergeometric series. How do we go? So thanks for watching, look forward to seeing in the upcoming videos too.